Okay, we're going to start doing centers of objects. And the objects we look at in this class will primarily be what we call composite parts. So we're going to be able to break down something into parts where we know where the centers are, and then we'll do some math on them to figure out where the center is of the overall object. More complicated systems would require integration. Now, at the end of this chapter, we'll do one example to kind of show you how that works. And it's really all the same thing, except rather than using blocks like I have here that you can easily get your head around, you have to use differential objects. And that's a little bit more involved. So, since you are just now taking your course in integration, we're not going to make you accountable for that. So, on an exam, you'll just have composite parts. For those that move on to the next course in dynamics, we will actually revisit this topic very briefly and just look at applying integration to it. So this is where we're going to start now. Basically, this is now fun time with blocks, okay? So kind of prepare to relive your inner child from way back when. So for this device, I have two rectangular blocks. This one is 8 by 8 by 4 units are feet. The top one is 4 by 4 by 4. And I've labeled them part A and part B. All right. So what we're going to do, the first step we do in this is figure out where the centers are of the shapes we can get our head around. So if we look at X, here's X coming out. This is a length 8, so rectangle, it's in the middle, 4. We have 8 along the Y, so 4, and then the vertical Z is up 2. So we can just write 4, 4, and 2. Now for block B, if we go along the X, it's 4, so half of that's 2. Along the Y, half of that's 2. But along the Z, the vertical part, you got to be careful. Notice, so the question is, where is its center? Where it's offset by 4, and then this is 4 high, so half of 4 is 2, so that leaves us with a 6. That's where the centers of the parts are. That's critical. All right. So what are our volumes? Well, we have 8 by 8 is 64 times 4 is 256. So let's see, we have feet, 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 feet cubed for our units. And then the top is 4 by 4 is 16 times 4 is 64. So the total volume we're working with, 256 plus 64 adds up to 320 cubic feet. This is big blocks, okay? So the first thing I want to do is figure out where the X center is. All right, so it's going to be a weighted average. How would we weight the average? Well, this one has a center of 4, but it has more volume. So that would get more weight in the model versus this one. So we're going to use the same equation we used the other day looking at Trump and George Bush. So let's just pose this. XV is, all right, so we're going to average these X's. So these are the things I want to average. This is like the scores in the exam, the 4 and the 2. So I have 4. Okay, what's its portion? 256 out of 320. Part B is plus 2. Okay, and what's its portion? 64 out of 320. Grab a calculator. 3.6 feet. Now, where's Y? Well, if we look at relative X and Y, there's symmetry here. So there's no reason to recompute this. There's YV. We're all done with that. All right, on an exam, I expect you to, if there's symmetry, you can simply make a statement. By symmetry, XV equal YV, and be done with it. If you're correct, you get full marks. If there wasn't symmetry and you claim there is, you lose a lot of marks. It's that simple. All right, now we move on to ZV. And so we want to average this one. So we have, for the bottom one, 2. And again, it's 256 out of 320. Part B is 6 in the air, and it's 64 out of 320. And we grab a calculator, we get 2.8 feet. So these are the centers of volume. Now I want to propose the following. Suppose that the specific weight, because we're dealing with American units, rho A is 1 pound, so that would be a force per foot cubed. And rho B, thing on top, is 3 pounds per foot cubed. So it's far more dense. All right, well, knowing that, so I can take volume, and so that says we're just going to put weight here in pounds. So the weight of the first one is 256 pounds, and the weight of the second one is 64 times 3, so that'd be 192. And now, then we'd have 498 pounds total. So now I'm going to ask the question, where is the center of mass? Now note, these things are relatively small, so gravity over the course of this thing is constant. Right? There's no variation in gravity that we could possibly measure over these two blocks. So when you consider that mass times gravity, being constant, is weight, all right, the numbers I have here are weight. I'm going to wind up computing CW. But because gravity is constant, that's the same as the center of mass. And people often talk about center of mass as they use the term center of gravity, which makes sense as well because if gravity is constant all over your device. So those are reasonable assumptions unless you're trying to figure out the mass center of Mount Everest or weight center, because then you might have variation. You would have some level of measurable variation in gravity, say, over the course of the height of Mount Everest. We're not dealing with that. So for us, center of weight, center of mass, center of gravity, all the same concepts. All right? So now we're going to, let me adjust my focus here. Field of view. I need a little more room to work. There. So now let's compute X weight. All right. So now it's the same idea. The center of A is at 4. Its contribution is 256 out of 448 plus part B 2. So same basic equation. It's just that our weightings have changed. And this one has 192 out of 448. And we do the computation. We wind up with 3.14 feet. All right. So what that's done is that's moved the center back a bit. Well, that reflects the fact that this is sitting here in this back corner here, and it's greater density. It pulls the average back. And again, we can appeal to symmetry. And there's the Y center of weight. Now we have Z, and so that'll be 2 times 256 and 448 plus 6, 192, 448. Apply the calculator, get 3.71 feet. So if you compare them, previously we're at 2.8, but that greater density brought the center of mass up quite a bit, nearly a foot. All right. So that's that problem. Now we're going to look at, here's another one. And I took this out of the text, former edition, maybe still in the new edition. I have actually no idea because I am way too lazy to go look in the book. I just don't care. So we have this doohickey where we're told this object has uniform depth into the page and constant density. All right? So it's all the same material. It's all the same depth. So if we knew the depth, we would know that the center of this thing would be halfway down. Knowing the depth, given a constant depth, halfway would be where the center was in terms of depth. we're not given the depth, so we're going to ignore it. Now, if we look at this, we see the coordinate system is centered here on this device. And so it is obvious from symmetry that the x-center is along this line. And so here's the x-axis going here. So x of I, so for all the various parts that I have in here, is at 0. So we don't need to compute that. That's obvious. So done. All we need to figure out is, for the coordinate system, where is the y-center. That's all that's left for us. And we're going to treat this point there as the origin. Okay? So let's do that. I'm going to we'll make that a little bigger to start. And so what we want to find for this problem is the center of area. All right. Now, since this is all the same material all through here, if we find the center based on the areas, because it's all the same density, you would have this same center of mass, center of weight, center of gravity. The only thing we don't know is the z part of this, because we don't know the depth, but that'll just be halfway. All right. So find CA, but we know that that's going to be 0 and then some y component. That's what we're looking for. All right, so let's start breaking this thing down. I've called this part 1, this part 2, this part 3. So the diameter of this thing is 50 millimeters. This thing goes 110 up, so that puts us from, if that's 0, 160, and this is 35 millimeters in diameter. So halfway up that is 17 and a half. So we have 50 and 110 is 160 plus 17 and a half. Says this is at 177.5 millimeters. This piece is 50. Half of 110 is 55. That leaves us at 105. Part 3, if this is 0 and that's 50 in diameter, 25. All right, now we need to do area. That's a circle. Pi times 107, not 177, 17.5 squared. So 35 is the diameter, half of that's 17 and a half. So pi r squared. For this one, now there will be a little bit of error here as this piece handles the curvature, but we're going to ignore that. So I have 110 times 15 is my area. All right. And then the last piece, diameter is 50. It's a circle. We have pi 25 squared. All right. Now in my notes, then you could take this, add it up, and you would have a total. So I'll leave this for you to do the math, but here's the basic equation. YA, not V, so we need to average these three y centers. And so this one would be A1, A2, A3. So you would have the following. 177.5 A1 plus 105 times A2 plus 25 times A3. And this would be a total, or A1 plus A2 plus A3. And if you do get your calculator out, you'll come up with 85.9 millimeters. All right, I'm going to reset here for a moment, and we'll do a couple more. Bye now.